Hello all, Vinod here from Entrance Engineering Academy. Again, let me discuss few questions from GATE XC 2021. Okay, so consider the fully developed flow of a Newtonian fluid. Density is rho and viscosity is mu through a smooth pipe. So here, a particular keyword in this particular question is pipe of a diameter d and length L. Okay. The average velocity of the flow is v. The length of the pipe is doubled. So what they are doing, the new length is two times of original length. That is what they given, keeping v, d, and rho constant. Okay, rho and mu constant. The friction factor will be dash. Listen, it's a very what I could say. It's a pretty good question. Okay, the first and foremost point here is um, the first and foremost point, instead of discussing the solution directly, I will just explain you the solution with the different variations of this question. Okay, so the reason is that will help the 2022 aspirant also, those who are going to prepare for GATE 2022 or 2023, that is for the future aspirants also, it will be helpful. Right. They said that it is a smooth pipe. So the first keyword is it's a pipe, and also they said it is smooth. Okay. Also they said it is smooth. Was there any word which is mentioning laminar in the question? Was there any word which is mentioning laminar in the question? No. Right. It is not mentioning. So obviously you should not take friction factor as 64 by Re. This is wrong. Okay, maybe you would have done this, but clear conceptual, if you want to understand it clearly, even if you use this also, you will get the answer correctly. Okay, but it is wrong. You should not use F is equal to 64 by Re for this particular problem because they didn't mention it is laminar. They simply said it is smooth. Okay, smooth pipe, then there both possibility are there. What are the both possibilities? The possibility is it can be laminar, it can be even turbulent. Okay, laminar means we know that friction factor is equal to 64 by Re, which means friction factor is a function of Reynolds number alone. Turbulent means two types are there, right? One is smooth and rough pipe. If it is smooth pipe, then friction factor is function of Reynolds number only. But if it is rough pipe, it depends on the average height of that particular roughness. But in this particular question, it is not rough pipe, so it is smooth pipe only. It is either, it's very simple, it's a smooth pipe. So either it is laminar flow or it is turbulent flow. The only factor here was the friction factor depends only on Reynolds number. Okay, it does not depend on average height of the roughness. That is what I said. Even if you use this formula and if you say that friction factor is depending on Reynolds number also, it is correct only. It is correct means it will give you the answer correctly. But in this question, they didn't mention that it is laminar. That is something which has to be noted. Okay, it does not mention laminar. So it can be laminar or it can be turbulent. Turbulent means it's a smooth pipe turbulent flow. So obviously friction factor is a function of Reynolds number alone. Okay. So this is the first conclusion which I'm making from this question. The first conclusion is friction factor is a function of Reynolds number alone. Now, maybe you would have done this mistake also, but there is a possibility still, even if you do this mistake, you will get the answer correctly. Now, the second mistake is something which I feel at least some 20% or 10% of the students would have done. Okay, but it is a very simple one only, but there is a possibility. They said length of the pipe is doubled. Okay, in some urgency, okay, in some urgency, we know that Reynolds number is rho v L by mu, right? In general, Reynolds number is rho v L by mu, where rho is density, v is velocity, average velocity, mu is what is that, viscosity. They said that density is constant, average velocity is constant, viscosity is constant, and this is L. And what is this L? This L is not length of the pipe. This L is characteristic dimension. I already discussed about this in our, I think it is in laminar flow chapter. Okay, so characteristic dimension or characteristic length. So L is not length in this case, it's a characteristic dimension. Okay, so what happens if, suppose, if you didn't understood this properly, or if you don't know that L is a characteristic dimension, then what you would have done? Okay, what is the possible mistake you would have did? As they said that length of the pipe is doubled, you would have taken that initial Reynolds number was initial Reynolds number depends only on length, and final Reynolds number is going to be proportional to 2 times of length. So Reynolds number is what is happening? It's becoming doubled. So if Reynolds number is becoming doubled, friction factor will become 1 by half. Okay, there is a possibility. So decreases by 2 times. You would have thought that this is the correct answer. Okay, would have thought this is the correct answer, but obviously it is wrong. Okay, it is not correct. Okay, because L is not length of the pipe. Okay, L is not length of the pipe. L is characteristic dimension. And for flow through pipes, okay, for flow through pipes, this diameter is there, right? Flow, that is for the internal pipe. That is for the internal flow. I'm sorry, for the internal flow. Characteristic dimension is d. So our Reynolds number will be rho v d by mu. For external flow, something like over a flat plate. Okay, I'm not drawing it properly. For a flat plate, L will be L, that is length of the plate will be L. But for this case, that is why I said this pipe is a keyword. Okay, pipe is a keyword for this question. Since it is a pipe, your characteristic dimension will be diameter. Now you could see that velocity is constant, average velocity is constant, diameter is constant, density is constant, viscosity is constant, so Reynolds number is constant. We already know, I already concluded that, right? What is that? What is the conclusion? Either it may be laminar flow or maybe turbulent flow. Friction factor depends only on Reynolds number because it is a smooth pipe, right? So obviously friction factor depends only on the Reynolds number. So as Reynolds number is constant, friction factor will also be constant. So the correct answer here is this one, that is it remains constant, that is remains the same. Okay, in this question, two possible mistake. First mistake is directly you would have assumed that it is laminar flow, but it is wrong. It may be laminar or it may be turbulent. The ultimately the final thing will be friction factor depends only on Reynolds number, because laminar also it depends only on Reynolds number. Turbulent also, if it is smooth pipe, it depends only on the Reynolds number. No issues. Second mistake, you would have taken L. Okay, instead of taking diameter as a characteristic dimension, you would have taken L as the characteristic dimension. If you have taken, then you would have got this. Okay, then you would have got this. That is Reynolds number will become double. That is also wrong. Okay, so these are the two possible mistakes. So correct answer here was option A. So let us proceed to this next question. See this question by using similar type of example. Okay, by using similar type of example, I explained the concept of what is that form drag and skin friction drag. Okay, so here also the similar question they are asking about form drag and friction drag. Friction drag is nothing but skin friction drag. As we already know that if I take a drag force will be classified into two. One is skin friction drag, which is nothing but friction drag as they mentioned here, plus another one is form drag. From the name itself, we can classify this. Okay, friction drag means it is due to form drag means it is due to the form. Okay, form of the body. Okay, it is due to form of the body, due to irregular forms. Okay, irregular forms due to the formation of eddies, that is circular motions. Due to those things, how much resistance it is offering. Okay, how much resistance those eddies, those irregular form of the body is offering. I'm not going for in detail explanation, I will just give an overview about it. I already discussed all these things in our course. Okay, so ff, form of the body, that is the friction, sorry, form drag depends completely on form of the body, how the body is oriented. Okay, so for this we have a best example. Initially we used to see, right, cars like this. Okay, initially we used to see cars like this, right, like a rectangular type or cubical type. But after that we started to get cars like this. Why? Why? This is obviously due to decrease the form drag. Okay, it is obviously to decrease the form drag. Okay, because of this irregular nature, there will be formation of more eddies here, and that increases form drag. Okay, when air flows like this. Okay, here due to the smooth flow, due to streamlining the body, form drag will decrease. Okay, let it be. Now coming for skin friction drag or simply friction drag, it completely depends on the shear stress. Okay, regarding this also, we already everyone would have studied in the chapter of boundary layer. Okay, due to shear stress offered by the fluid, suppose air. Okay, suppose air is flowing over the body due to shear stress offered by the air on the body. Okay, shear stress offered by the air on the body. Due to that shear stress, there will be some resistance against the motion, right? So obviously, drag is something which is resisting the motion. Okay, so if the drag caused due to shear stress, it is going to be friction drag. Okay, then we already know that shear stress majorly is associated with viscosity, so that is why the name friction comes. Okay, that is why the name friction comes. Okay, something like this is associated with viscosity and the shear stress, and this is associated with the form of the body. Okay, how the body is oriented. So combinedly, this two is what total drag is. Okay, I explained the basic concept which is necessary. Now let us go for the question. Two orientation of the finite flat plate are shown in the figure. In orientation 1, this is orientation 1, the plate is placed perpendicular to the flow, while in orientation 2, the plate is placed parallel to the flow. If the velocity v of the air in both the orientation is same, okay, this both are same, which one of the following option is true? Okay, very simple question, to be honest. If you understood this concept, and I given the same exactly the same example when I'm discussing this concept, exactly I taken the same example of a flat plate and I placed one plate vertically and another plate horizontally. Obviously, what will happen if you start imagining the flow pattern? The flow pattern will be something like this, right? Here there will be lots of what I could say, there will be lots of free spaces where there will be very high formation of eddies. Okay, but if you take this case, there will be smooth flow because the this particular plate was in line with the flow. Okay, it is in line with the flow, so the formation of eddies here also, the eddies will be there, but comparatively less, very less. So now you could answer very easily. Orientation 1, eddies are more, so obviously form drag. Okay, eddies are more, so obviously form drag will be more. And you could see the area of contact was less, right? Very small area was in contact, right? But here you could see large area was there in contact with the fluid. So here shear stress will be more because large area was there in contact. So not shear stress will be more, the force. Okay, that is Fs, skin friction drag, which is due to shear stress. Okay, here there was a large area of contact, so skin friction drag, which is due to shear stress, will be more. Here less area of contact, so here Fs will be less. So it's very simple. Fs is going to be less in case of orientation 1, and orientation 2 form drag will be less. Okay, but skin friction drag will be more. Why skin friction drag is more? Because more area of contact. Okay, more area of contact. As there was more area of contact, skin friction drag, which is due to tau, will be more. That's it. So let us check out the option. Which one is correct? Orientation 1 has higher form drag. That is correct. And lower friction drag. That is correct. Orientation 2 has lower form drag. That is correct. And higher friction drag. That is correct. So option A is correct. Straightforward. Okay. All the other options are wrong. So orientation 1 has higher form, lower friction. Orientation 2 has lower form and higher friction. Okay. So let us go for the next question. Okay. So here they're asking the head loss scale associated with flow entry of the water to the internal passage depends on the shape of the entry. Okay. So the following figure shows the three different types of flow entry into a pipe. Which one of the following relationship correctly represent the head loss associated with the three different flow entries. Okay, listen, when flow enters, okay, it has to flow without any obstruction. If you take A, B, and C, it's very clear that C has a smooth corner. Okay, C has smooth corner, so flow can happen very smoothly without much of an obstruction. So obviously, their head loss will be less. And if you take option A, compared to C, it is not smooth, but still obstruction will be less. Okay, obstruction will be less. It can flow. Okay. Now, if you take B, what will happen? There will be lots of obstruction, right? Because of this, there will be lots of obstruction, which is not desirable. So obviously, head loss in case of B will be more compared to all the other cases. So maximum head loss will occur in B. Okay, this is going to be maximum of all. And next to B, it's going to be A. Okay, next to B, it's going to be A, and next to A, it will be C. So C is going to be the minimum one. Okay, it is going to have the minimum one. So the correct answer was BAC. Okay, BAC. So which is option D. Okay.